mean, it would be good as give some sort of excuse to tell a little bit about what noncommutativity is, and also to tell what are the problems and what is the meaning, or what might be the meaning of causality, and what is the difficulty there. Okay, so there's some plan. And I started with a quote, big quote from Alain Kohn, who is the founder of noncommutative geometry. So noncommutative geometry, if you think about it, is rather new in terms of mathematics. It started something like 30, 35, 40 maybe years ago. Of course, the idea came back a little bit earlier, but the original proposals were around the 80s of the last century. And okay, so in mathematical terms, this is something brand new. So the quote is that explains a little bit what is noncommutative geometry. So noncommutative geometry at the moment you can think of as a collection of examples, collection of mathematical examples that come from different parts of mathematics. And those different parts of mathematics, also physics, like phase space in quantum mechanics, which is no longer description as a space, but rather description in terms of operators on a Hilbert space. The mathematical descriptions of something which is like something like quotient space, some quotient spaces. This also requires some additional structure, some other better description than in terms of points. And also the space of foliations. So imagine foliations, so something like some very sophisticated submanifolds in compact manifolds. And okay, there are some non-abelian discrete groups with the abundance of discrete groups, space of Penrose tilings. If you know about Penrose tilings, you can think about all possible Penrose tilings, and then you can think it's a space, and actually it's not a space. You can better describe it in other terms. Well, some physics motivations, like from solid-state physics, M theory, string theory, whatever. All right, so this is this abundance of some examples, and then there's a sort of a common idea behind them, and this idea is that to have a better description of them, to have nice description, one needs to go beyond the ideas that are so to say imprinted in our nature, the ideas that relate to the space, to the concept of point, to the concept of, well, in mathematics, of topological space, of a differentiable manifold, and so on and so forth. So this is basically what it is. This is long justification, but I think it gives some flavor. Well, there are some models of space-times, and I will say a little bit about those models and a little bit about all those implications. Okay, so what is the physical motivation, or some physical idea that noncommutativity might really be good or maybe better? And okay, there are various arguments. One of the arguments, which is, so to say, probably most famous, is also not very old, 95, given by the Doppler, Fredenhagen, and Roberts, so basically known under DFR construction, which gives a following argument for the existence of noncommutativity. So first imagine, well, take what we know. So take quantum mechanics. Quantum mechanics, you know that you cannot precisely localize particle or something, in space. You can localize, but of course, you have the uncertainty relation, then the uncertainty in the moment gets higher and higher. And of course, this localization needs higher energy. So this is quantum mechanics. This is basically the lesson from quantum mechanics. Now you have general relativity. From the other hand, you have general relativity, which tells you that if you have enough energy, say mass, but mass is equivalent to energy, you have energy localized in small, so say, piece of space, then it might lead, or it would would necessarily lead to the creation of a black hole, so collapse. And of course, that would mean, this is some sort of contradiction. And then one can use this. Here it's just hand-waving arguments, but if you look up the original paper, you can make it a little more precise mathematically. And you can use these arguments to show that in the end, what one derives from all those two things, one can derive some uncertainty relations between the coordinates themselves. What does it mean? I mean, this is the DFR model, so say commutation relations that come from these uncertainty relations. I mean, this is a model that gives this uncertainty relation. The uncertainty relations are a little bit more complicated. Just if you're interested, look at the paper. And, I mean, they are like the phase space of quantum mechanics, a little bit different because this Q doesn't necessarily to be constant, it just needs to be a central element, so it could be more complicated. But it's just, I mean, I wouldn't say it is a derivation, it's a solid theory, it's something we can predict from those two things. It's just an indication that if you try to marry general relativity and quantum mechanics, you might necessarily come to something which makes the coordinate don't commute, which means that we are not really working with a space, because the coordinates are nothing but functions on a space, and of course functions on a space do commute. So in this case, I mean, we cannot have a space. Okay, there are some other arguments. There are some arguments coming from string theory, M theory, that lead to the noncommutative target space of the Moyal type. And then there's a hint coming from the description of particle physics, from the classification of all the interactions and the structure of all the interactions. And there's a very nice interpretation of that as originating from some sort of small noncommutativity. Small in the sense that it's very mild. It's just, sometimes sort of finite part which is noncommutative. All right, so this is just the motivation. Now, what is it all about? And this is basically what I like to concentrate on in this first part is just, the language of noncommutative geometry. And the language is quite easy. I mean, you basically look at the things you know and try to express them a little bit differently. So, if we have a space, so the so-to-say classical notion that one usually starts with is a space, so a collection of points with some additional structure. Now, if you have a space, say topological space or manifold or whatever other space, you have also functions, which are just maps from the space, satisfying certain conditions or not, to, say, real numbers, complex numbers, whatever field. And it appears, and it will come to the little bit more precise ways, that you can basically replace one with the other. So instead of talking about a space, you can talk about functions, and instead of talking about a function, you just take space and it gives you both. All right. Now if, for instance, this additional structure that comes is just like if you have topological space, you have topology, so you can talk about continuous functions. If we have structure like measure, you can think about measurable functions. If you have differentiation, so you can add more and more structure, or less and less structure to that. If you have differentiation, you can talk about smooth functions. You can generalize the ideas and extend the ideas to some other constructions. So for instance, you have products of spaces, you can think, what it actually leads to for the functions. If you have some more structures like some bundle structures, fiber bundles, then you can think of, okay, what's the equivalent for the description? These are the sections of the fiber bundles. If you have something that in physics one really, especially in differential geometry and general relativity, one lives, these are vector fields, then you can think of vector fields, replace them by the dual object, which are differential forms. And you have differential operators, which basically, like Laplace operator, like the Dirac operator, which in fact, in this description, become just operators on some Hilbert space, on a Hilbert space. So this is basically, I wouldn't say the dictionary. It's just, the notion of some words that appear and the path that one takes to come from the classical description, the description that one is used to the description of noncommutative geometry. Now, just to make it a little bit more precise, let's start with topology. So, the idea is that, as I told you, one really lives with, if you have topology, a topological space, you can have the algebra of continuous functions, and then you can ask, well, what is the structure of this algebra of continuous function? And the structure is that of a C-star algebra. So what is the C-star algebra? And this is, the point that you can actually define it in some abstract terms. So what's a sister algebra? It's just an involutive Banach algebra, complex normed algebra. So it's an algebra which is equipped with a norm, and it's complete as a topological space in this norm, and the norm satisfies certain additional relation. All right, this is an abstract thing, and what one knows, and there'll be, this is actually in the example, if we have X locally compact Hausdorff space, then you have the algebra of continuous functions on X.
Excuse me, what is the star in the A star?
Oh, this is an involution in the algebra. Involution in the algebra. Basically, if you have complex valued functions on a space, this means just complex conjugation.
It's got the black one.
Yeah. All right, so this is just the classical and so to say standard example. If you have locally compact Hausdorff space and you take the continuous functions, then C of X is a commutative, not necessarily unital, so there's not necessarily unit in the algebra, C-star algebra. Now, if you look carefully here, and this definition, I mean, this is just an example of an object that satisfies this definition, then you see that there's one word that appears at the bottom, which doesn't necessarily appear in this, so say, pink area. And this is the word commutative. So if you think about spaces, then all the algebras of functions that you necessarily obtain are commutative algebras. Commutative means if you have two product of two objects, it doesn't depend on the order. Whereas in the definition is just abstract. It doesn't require a thing to be commutative. So this is what made the idea, to look at the C-star algebras, not necessarily commutative, as some sort of generalization of what spaces are. So what is the example of, the simplest example of something which is non-trivial, non-commutative, and the C-star algebra, and this trivial example is just you take the matrices. The algebras of matrices, I mean, here I've taken the finite direct sum of finite dimensional matrix algebras, and this is, sort of the easiest object you can think of, is this object you can work with. There are some more nasty or more advanced or, so to say, more interesting examples. I mean, this is, object which is, say, finite. I mean, as a vector space is finite, and of course, as an algebra, it's finite. The thing is, I mean, and this is the example that, if you think about quantum mechanics is some sort of natural, you take a Hilbert space, and you take all bounded operators on a Hilbert space, and taking separately Hilbert space and all the bounded operators with the operator norm, then you have necessarily a C-star algebra. It's a huge one, but it's a C-star algebra. And of course, it's non-commutative. There's another, you can take of compact operators on a Hilbert space. So basically, this is a closure of the operators of finite rank. So think of this, if you can think of this algebra as some sort of algebra that you can actually represent on a Hilbert space, just represent this thing as matrix multiplication on some vectors, or finite dimensional vectors, and you just extend it by zeros on the rest, then you can have some operators of finite rank, and if you try to complete them, you just get the algebra of compact operators. These are something like, you can think of them as some sort of small operators on a Hilbert space. It's just a two-sided ideal in B of H, and so these are two extremes if you think about a Hilbert space. This is, say, smallest C-star algebra, and so say the largest C-star algebra of a Hilbert space, and those things, I mean, that live in between. All right. Actually, the background, and so say the motivation of noncommutative geometry could be contained in this topological noncommutative geometry, so related to topology, to continuous functions and C-star algebras, could be phrased or could be contained in two very important theorems of Gelfand and Naimark, and the second, also GNS contraction, so Gelfand, Naimark, Siegel. But the two theorems of Gelfand and Naimark state two most important things, and these theorems, I mean, date back to the 40s of last century. The first one is that if you have a C-star algebra, so the definition that I gave you, there was a definition that was very abstract. You had an algebra, so there's basically a thing with objects that you can add and multiply one by another. But this is an abstract definition with some norm and so on. But then this first theorem tells you that basically every C-star algebra is just an algebra of some operators on a Hilbert space. So whenever I have an algebra, C-star algebra, I can think of it anytime as bounded operators, as some subalgebra of these bounded operators on a Hilbert space. So in effect, I mean, every algebra of this type is necessarily, I mean, something like comes with a Hilbert space and could be interpreted like that. And there's a second theorem, which is, I mean, relates to what I said in the beginning, that if you additionally have this C-star algebra and you add this word commutative, then there's something which is called Gelfand transform, and there's a Gelfand spectrum of this algebra. And basically the statement is that this algebra is an algebra of continuous functions on some topological space. So whenever you have so say bottom line of these two theorems is the following. I mean, whenever you have a C-star algebra, these are operators on a Hilbert space. And the second is whenever you have a commutative C-star algebra, then there is a space behind. These are always the functions on a space. Now, forget about the word commutative, and you can think, okay, we have some sort of, in quotation mark, noncommutative spaces. What are the noncommutative spaces? Of course, the noncommutative spaces are not described in terms of points and the properties of this collection of points, but are described in the properties of what you can call functions on those things. But those things don't exist. What exists are only, so to say, functions, so the C-star algebras or the algebras that you can think of functions on those non-commutative objects. Okay, and this is basically the, so to say, the background, the ground on which non-commutative geometry is somehow built. Basically these two theorems. So, going next step, you can try to make some parallels between the objects that you know and the objects, this generalization of these objects. So just as I said, I mean, this Gelfand-Naimark theorem gives the equivalence between, say, locally compact, or you can say compact if you have unital C-star algebra, topological space, and a C-star algebra. And then you can, try to go on mapping other objects, properties, transformations, everything. So for instance, if you have a homeomorphism, so a continuous map between two topological spaces, this also, so homeomorphism between from X to X, then you have an automorphism of algebra. Generally, if you have proper maps, then you have morphisms. If a compact space is a unital C-star algebra, so a C-star algebra that has a unit. If you have an open dense subject, you have an ideal or essential ideal. Compactification is just unitization, so adding a unity, extending the algebra so it has units. Don't check compactification, multiply algebra. If you have two spaces and you think about Cartesian product, then on the level of C-star algebras you think about the tensor product, and so on and so forth. So you can make this dictionary, extend the description of one thing using the other. So the basic idea, non-commutative geometry, is just you forget about this thing, cross it out, just work only with this, and extend it and forget about the word commutative. And then you have the idea. So it's sort of change of paradigm. Now, this is a next step, a next leap that's been done by Alan Kohn in the 80s, and basically in the 80s and in the 90s, is to go a little bit forward. To make an extension, I mean, the thing that I said is about topological spaces. Topological space is very nice. Topology is a fascinating thing. But basically, I mean, if you take a ball, squeeze it a little bit, take another metric on a ball, you still have, topologically, you still have a ball. So it doesn't see what physics is interested in, so it doesn't see the metric, the distances, I mean, all the things that are relevant, say, for physics, for the description of the universe. So what one needs to basically extended notion that, I mean, comes from topology to the realm of differential geometry. And differential geometry tells you about something which are manifolds, so spaces which has some extra properties, extra smoothness, extra behavior, and well, look quite nicely, and one can do a lot of things with them. So now we know that we work with an algebra, so how to encode the things that we are working with in this language, in the language of algebras. And this is a proposition. I mean, there's been several propositions that go along this way, several descriptions, several models, several examples. This is a proposition that has some mathematical motivation that has been proposed, as I said, by Alan Kohn something like 20 years ago, roughly, and it's been developed since then. You know, this is a notion of so-called, I mean, the wording spectral geometry is not really correct because it could be used for some other things. Something like spectral triples, spectral geometry, spectral description of the world, of the noncommutative manifolds. Now, what is it? So, what do we start with? I mean, as I said, I mean, the idea changes. We don't start with a space. What we start with is an algebra. There's an algebra. We'll not start with a sister algebra. There will be just a subalgebra of a sister algebra, just as we cannot start with continuous functions because continuous functions are not differentiable. We need to start with something smaller. So we start with some algebra, but the thing is that we need to have it represented on a Hilbert space. So basically, what we have is an algebra that is thought of as operators acting on a Hilbert space. And then we introduce the notion of a geometry. And this geometry comes, well, you can encode the geometry in different ways. But for instance, I mean, if you look around, I mean, on a manifold, how you encode the geometry, where, say, you encode it in a metric, I mean, just naively, Riemannian geometry is encoded in a metric. And how you encode the metric, well, there are various ways of encoding metric, but for instance, you can encode the metric, to some extent, in the Laplace operator, or you can encode the metric in, well, metric tensor, but metric tensor, I mean, gives you the Laplace operator or Dirac operator. So here it comes in terms of Dirac operator. So Dirac operator is a self-adjoint operator on a Hilbert space. So we encode the geometry in this example, in this model, in this construction, by saying that we have a self-adjoint operator which satisfies certain conditions. And then you may like it or not. This is just like imposing, you know, some sort of axioms. And actually, I mean, in some papers, these are called the axioms of noncommutative geometry. Well, axioms or not, this is just a proposal, but this is just a model. How can one think of geometry? I mean, if you look at the definitions in differential geometry, I would say they are axioms, but they are some objects that are defined by their properties. This is just like that. So this is a new proposition for geometry which extends beyond the classical one. So what are these axioms? So what are these conditions? They look very technical, but they make good sense. First, good sense mathematically. They have very deep motivation coming from some part of studies of algebras and studies of objects like K-homology, K-theory, and all that. So there's a good mathematical background, good motivation, and basically, I mean, they are not very, very complicated. So what are the conditions? So first, what do we take? We take that the commutators of D with any element of the algebra is bounded. That the inverse of D is a compact operator. Compact, I told you what are the compact operators. This is the, so say, the smallest algebra, sister algebra, that you can have on a Hilbert space. And telling that D inverse is compact, I mean, it has some consequences. You can say it's small. I mean, here, I mean, it was assumed also that its kernel is not zero, so you can make it invertible. It doesn't really matter. This is a technical point. But this also tells you that something, I mean, there's an interpretation of this D inverse as some sort of a length scale. If you look at the dimension, the inverse of D has the dimension of a length. So this is something like a minimal length or the scale length of the model. Now, I mean, of course, there's not length in terms of you can give it as a number because this is an operator. So this is something different. Now, there are there are some additional things, like you can think of spectral triplets that are even dimension or odd dimension, and there's a additional thing that comes with the even dimension, which is Z2 grading, and so in physics you can call it something like gamma 5, some sort of Z2 grading that anti-commutes with this D. There is a definition what makes this spectral triple real. So there's additional thing like additional conjugation that makes it additional real. And there's something which is called an order 1 condition, which tells you that this J, which is just an operator, anti-linear operator, maps the algebra to its commutant, and there's a additional condition that the commutators do commute with the things that are conjugated by J. I mean, again, you can think of it very weird, very, so to say, highbrow, whatever. What does it come from? Where does it come from? What is the idea of this? This is just a set of axioms, pulled out of a hat, and you telling that this is geometry. Well, there's a very good motivation, and the motivation is the following. So if you take a manifold, spin Riemannian compact manifold. So this is the first warning that I give you. I mean, we're talking about Riemannian geometry, so Euclidean geometry. No Lorentzian signature yet. So we're talking about compact manifolds. So, I mean, you can also ask, I mean, what it has to do with physics. I mean, because we're talking about things that are compact, so something like a sphere, like a torus. So if you take a Riemannian compact spin manifold, yes?
What does spin mean, please?
Oh, this is, it means that there exists a spin structure over the manifold. So this, I don't know whether, this is just answering the question by some term. Yeah, okay. Yeah. So if you have the section, so basically you have a spinor bundle, that behaves quite nicely, that you have a vector bundle of spinors over the manifold that behaves quite nicely under some transformations. So if you take the Hilbert space, there are sections of the spinor bundle. So basically at each point you have a spinor, and the sections are something like locally functions from the manifold or from some environment of a point to this spinor bundle, and you complete it, and you take a Hilbert space. Then you take the Dirac operator. So you have a Riemannian spin manifold. So Riemannian means there's a metric. With the metric comes the Levi-Civita connection. With the Levi-Civita connection comes the spin connection. That is basically all unique. And with the spin connection, one can uniquely construct the Dirac operator. And this is a unique operator that you have. And this Dirac operator is then, there's a theorem, this is an operator on this Hilbert space that satisfies all these conditions. So in addition, if your manifold is even dimensional, you have this gamma. In addition to if the manifold is spin, then you certainly have this J. In physics, it's called complex conjugation. And then the theorem is that this is a spectral triple with real structure, so real spectral triple. So shortly speaking, this is a motivation. Classically, manifolds are described in these terms. And of course, this is just, the theorem that's stated here is one way. So once you have this thing, so classical geometry, you have this. But there's a little bit more, the so-called reconstruction theorem, which adds to it with some certain additional assumptions and little bits of analytical stuff and all that. I won't go into details, but basically tells you that there's an equivalence. So simply means that instead of describing the manifolds just by, how you describe usually manifolds, making maps, gluing things, so making maps into Rn, gluing things, constructing everything, locally and so on and so forth, you can construct it this way. You can just construct it in a sort of abstract way, and construct it in an abstract way, specifying all those conditions. So this is a reconstruction theorem. There's been several attempts to prove it. Finally it's been proven by Aaron Kohn, something like 3 years ago. And basically, it states that equivalently, classical geometries, classical spin geometries are described in this funny, abstract, sort of not, absolutely not natural terms, but algebraic terms. So, okay, classical motivation is one thing, but the good question is, do we really have examples of something which is non-commutative? And the answer is yes. So this is the definition. So this definition of all those things is something that one can actually extend and make, I won't say a plentitude, but at least some quite interesting examples when the algebra that you have is not commutative. It could be mildly non-commutative, something like a commutative algebra tensor with some matrices. It could be highly non-commutative. There are some very nice examples of highly non-commutative algebras that you can have with, and you can have the examples of those, say geometries in this sense. So this is just an attempt to extend the differential geometry from its classical setup of spaces, manifolds, to the spaces, to the realm of operator algebras. So once you have an algebra, which is some sort of operator algebra, then you can think of differential geometry in this term. This is a proposal. It's not a theorem that you can always have it. It's just a proposal that what you can call as a, say, non-commutative manifold. All right.
In this theorem, it states that there exists such n,
Yes.
yes?
Yeah. So the theorem is that if the commutative algebra... that there exists such M, yes. Yes. I mean, there's a lot of other assumptions that come into it, but yes, this is the theorem. Right. Now, the spectral geometries are applicable to non-commutative algebras. If you have the Dirac operator, then classically it gives you a metric. It's a very nice formula that expresses the metric in terms of distances between points. Actually, I mean, as the things that are related to Dirac operator, and this is very, very, very easy formula. I mean, the distance between 2 points is just the supremum of all these, so to say, values of possible functions on x. So x of a is just, so think of a as a function. So x of a is just value of function at x. Y of f would be the value of function at y. So you take the absolute value of the difference, but you take the supremum of over all functions such that the norm of the commutator is less than or equal to 1. You can think it, in classical terms, you can think of it as you can take the supremum of all functions that gradient is less or equal than 1. So if you have function that, grows, not the rate of growth is not bigger or equal to 1, then this is satisfied. Now, the second thing is that you have a very quite good, quite reasonable differential calculus. I mean, this is FODC, means first order differential calculus. It could be actually extended to higher order, but I mean, what's really necessary at one point is the first order. And then, this assumption that this is compact means that we actually, for the compact operators on a Hilbert space, there's a fantastic thing that one can use a lot of so-called exotic traces. As you know, if you take operator on the Hilbert space, the spectrum could be, it's an infinite sequence. So, trace might not exist. But the thing is that for some operators, they are not the, usual traces like the sum of all the eigenvalues, but there could be some very exotic traces. And there's quite a rich theory of these exotic traces. And apparently, this theory, these exotic traces appear here and play a significant role. So, for instance, that you can say something as, well, say, sort of non-commutative integral of a function, and this could be some sort of this exotic regularized trace of something like just a function multiplied by the absolute value of d to some negative power, and this negative power is the metric dimension of this space. So you have a lot of very rich structure that comes from other part of mathematics that could be used here. All right. So, for instance, what are the exotic traces? Just to give a sort of a flavor of it, what it is. So, what was this? You had an operator with some eigenvalues. So, mu I of t are the eigenvalues of this operator. So, you just take the sum, but you don't take, usual trace would be just the sum of all the eigenvalues, but it might not be, a series that's summable. So, what you take, you sum from I to n, and you normalize it by the logarithm of n. So you just take this sequence, and you take the limit as n goes to infinity, and the exotic trace exists if this limit, exists. It's not and is finite. So this is just a very easy example, and just reminds you of something. I mean, this is a procedure that one might call sort of regularization. So this is, in a way, quite relevant for physics. So the other way of expressing this is by residues, and taking an unbounded operator such that the universe is compact for some sufficiently large real number greater than 0, the absolute value of d to minus r could be, and in many cases is, and this is a theorem for the manifolds that for the Dirac operator over manifolds, it is trace class. So it is so small that it's really trace class. And then you can just consider the so-called zeta function related to these operators. Zeta function d of z is just the trace of d, absolute value of d to minus z. This minus z is just a complex number with the real part which is bigger than r. And by some general theorems, this will be an analytic function on a large part of a complex plane, and then you can extend it. And you can extend it to the entire complex plane, and there will be some poles, and at these poles there might be some residues, and you might think about, computing the values of the residues at those points. And it appears that if you do it, I mean, then you would get also the examples of very nice functionals, very nice traces. All right, so I mean, I maybe skip it. I mean, one of the, so to say, nice examples and very relevant, I mean, also for physics examples, is so-called Wojcicki residue, which is defined for pseudo-differential operators on manifolds. And this is just a special case of all that. The other trace that I showed before this is the Dismir trace, and there's a relation between them. So actually, I mean, they are all related to by some, well, easy relation. Okay, again, the bottom line of this part is that when you pass to the description of the, say, geometry in terms of operators on a Hilbert space and the properties of these operators, you suddenly have a rich mathematics to use. And this mathematics is quite relevant. Okay, so how to use it for physics? That's quite easy. I mean, what physics is, mostly, is just looking at some functionals over the, say, space of possibilities. So it's looking for something like an action. You have some configurations of your system, configuration of your field, and you're looking for some functional. You're saying, okay, we're looking then for minima or whatever extrema of this action. So the thing is, if the geometry is described by one single thing, by the Dirac operator, by one single operator, then what you need to look for some functional over the possible space of all those operators. So for instance, I mean, if you take a manifold, then the space of possibilities would be the, say, Riemannian matrix on this manifold, and with this Riemannian matrix you get the Dirac operators, and that would be just a functional over that. All right, so how to make the simplest possible functional? You just do it like that. D square, well, it's an operator on a Hilbert space. On operators, well, nicely defined with some nice properties, you can always use the functional calculus, so you can take any reasonable, I mean, okay, there's some power in this statement, reasonable function of this Dirac operator D, and it might happen that the operator you get is an operator of a trace class, so you can compute just the trace. And for instance, f could be a cutoff function. What does it mean, cutoff function? You just compute, for instance, the sum of eigenvalues, or just compute the number of eigenvalues up to some level. So, for instance, you say 100, and you look, okay, how many are the eigenvalues of the operator D which are less than 100? You can put 1 million, and the function will tell you how many eigenvalues are there of this operator which are less than 1 million, and so on and so forth. Of course, I mean, so to say, when you go to geometry and the physics related with the geometry, then this cutoff has some scale, and this would be the scale of energy. So for instance, it would be like calculating the number of eigenvalues less than certain energy. All right, so this is the idea. Now you can ask, well, can one compute it? And the fantastic thing is one can really compute it. So if one takes, for instance, exactly some scale lambda, say energy scale lambda, whatever, a cutoff, could be Planck or could be the mass of Higgs or mass of whatever, and you try just to compute the number of eigenvalues of a Dirac operator on a manifold less than lambda, well, d squared less or equal d squared, lambda squared, then what you come up is sort of asymptotic expansion, so you get terms that are proportional to lambda to the, this is for a 4-dimensional manifold, as physics is motivated by dimension 4, still Riemannian case, Euclidean case, no Lorentzian signature. Then what you come up is the terms which are lambda to the power 4th, lambda square, and lambda to the power 0, and there are terms that are you can neglect, you can think of as small, 1 over lambda square, and so on and so forth. But those three relevant terms, which are lambda square, lambda 4th, and lambda to the 0, are actually giving you some information about possible physics. So lambda would be something like the energy scale, so it's some sort of fixed scale of an eigenvalue.
It's not a cosmological constant.
No. The thing is, I mean, so what are the terms that you get? So the first term, as you can see here, is just the term which has some lambda square, lambda 4th, lambda square, lambda 0, but has here the integral of square of g d4x. This is just volume. So
C and D are constants with certain dimensions.
yeah. So this is, so F, I wouldn't go into what's F2, F4, and F0. There are some constants that are related. Basically, they are so-called momenta of this function F. If you take basically not any function which is just a cutoff, but take its smooth function, then that's the momenta of this. Basically, this depends only on this momenta of this function. So this is the volume term. Well, what is the volume term if you take an action in cosmology? This is just a cosmological constant term. This is just a cosmological constant term. Then there's a second term which comes from lambda squared 0, and this is just the Einstein-Hilbert action. And then what you become as a next term, so to say order term, is some Weil tensor square and some term which relates to Ricci and Riemann curvature. This is a term that probably you might not like. This is a, so to say, higher derivative addition to the gravity. But I mean, it just appears here. I'm not saying this is good, bad, it's physical or unphysical. It just appears here. So this is if you take a manifold, pure manifold, nothing else. Well, what happens if you slightly extend the manifold by something non-commutative? And this slightly non-commutative thing would be just a finite dimensional algebra of the type that I presented, something like a finite sum of matrices. Actually, the algebra that one thinks of is just complex numbers plus quaternions plus 3x3 matrices. This is just, the model that one can think of. But I mean, it could be something similar. So then what one gets, well, there comes an entire theory that comes an additional field, which is actually not something like a scalar field, but say it's basically a Higgs field. And you'd have the square of the Higgs field, where the kinetic term of the Higgs field, the term which coupled Higgs to the scalar curvature, and with those finite things you get the gauge theory. You get basically the Young-Mills action, and finally you get the 5 to the 4th, so something which is compatible, which is responsible for the Higgs potential and the Higgs and the breaking of and the symmetry breaking. So, in a very, very simple model, using the principle of noncommutative geometry and using these tools of what's called spectral action, computing the action over the space of possible Dirac operators, what do you get? You get basically the contents of the particle physics that one knows, so the standard model. Of course, I mean, you put a lot of inside, but then by some geometric principle, you get those answers. And you get the classical gravity. Well, classical gravity bears some terms that, well, might appear to be not relevant, But anyway, I mean, this is it. And with cosmological constant, it might be non-zero. All right. So far, okay, since this been the, so to say, long introduction, now I'm trying to, to find the answer. Okay, this is very nice, but this is all Riemannian, not pseudo-Riemannian. So this is all Euclidean. There's nothing to do with physics. Okay, I mean, you might say, I mean, then we get this result and we make some sort of weak rotation, I mean, going to the signature, which is the Lorentzian one, but okay, I mean, this is, might not be the right answer. Okay, so how about Lorentzian? So can one have this Lorentzian definition of geometry? So this definition of geometry that's been proposed by Kohn for the Euclidean one, but adjusted to the Lorentzian case? And the answer is yes. It's been done by myself and Mario Paschke some time ago, and this is based also on the ideas of some other people like Gracia Bondia and some others. And this is basically, I mean, not very sophisticated one. It's sort of easy. So this is the proposition, the definition of the spectral type of signature 1Q. Q could be some number 1, 2, 3 or higher. And basically the data is just the same. A, the algebra representation, Hilbert space, Dirac operator, reality, gamma, if the thing is odd or even. If the thing is even, if not, there's no gamma. And the only addition is some beta, which you can think of as some sort of time orientation that's given. Why? So basically the axioms are just the same. So the only thing is that, well, there are some other commutation relations. This beta is just a Z2 grading. Actually, it gives the structure of the space that you have, the Hilbert space, so-called Krein space structure. It's just, some sort of additional product that you can have on this space. Then D is unbounded density defined operator, but we don't assume that this is self-adjoint, but beta self-adjoint. It just simply means that this beta D would be self-adjoint, while the commutators are bound and so on and so forth. Then for the compact resolvent, so for saying that the operator is small, we don't take D, because D, of course, won't be of this type, but we need to take DD star, so we need to use this beta, this Krein structure, to actually define it. And the only thing is, I mean, that there are some very nice changes in signs for the relations between all those operators. Because, I mean, all those operators have some predefined commutation rules, I mean, that have these signs, and this is all that you need. And then the theorem is that once you have a Lorentzian geometry, then you have a Lorentzian spectral triple. This is this Krein structure, I mean, has to satisfy some certain additional conditions. The Dirac operator satisfies the order 1 condition. And why I say that this beta is just a time orientation, because, I mean, one can say that this Lorentzian spectral triple has time orientation if this beta is just a 1 form. It's basically an image of a 1 form. It just tells you that there's some predefined sort of direction that could be interpreted as time direction. I mean, this has nothing to do with real time in a way, because that could be noncommutative. It's just, sort of a operator type time, but still it is possible to do it. Well, there's something which could be added that, I mean, could be a little bit restricted. You don't need to have spin case. You could only have, so to say, modulus 2 case. So you don't need to have the, so to say, signature 1Q. It could be 1Q modulo 2. This is not really the thing. Okay, before I finish, how much time do I have? Something? 2 minutes. Okay, so I'll be very, very quick. So, okay, so these are the definitions. This is, I mean, basically showing that you can do it. Now, what about things like causality? And this starts a nightmare. And the good thing to start to look at it is just you look at quantum field theory. So if you look at quantum field theory, there are several notions of causality that are adapted to the notion of quantum field theory. There's something that's called Einstein causality, macro causality, micro causality, and basically all of them are actually related, with the exception of macro causality, to the notion of points. So you have some points that are space-like separated, and then you say this has some properties for the fields or for the values of the fields. Now, the only thing that doesn't use doesn't use explicitly points is the macrocausality, which just relates the causality to some, or locality to some analytical properties of the S matrix. And this might be the only hope. Now, in noncommutative geometry, there's no notion of points and locality. In fact, all the theories could be just thought of as some non-local theories. So the only hope would be the approach by the S matrix. But what is the scattering? What is the S matrix? For that, you need some models for field theory. You need to solve the S matrix, find it, and so on. So the thing is that people started was to use the approach for non-local field theories and try to get some insight. Now I tell you, the contradicting results. I just glimpse you some of the results, which are restricted to the case of so-called Moyal deformation, which is basically something like, imagine this is just a phase space, but you're doing the geometry of the phase space. So this is roughly like Moyal deformation. So some sort of a space when you have the coordinates x mu, not commuting, but commuting to a constant. So there are 4 results that I can cite. So first by Balachandran and collaborators, which is basically negative violations of causality. On the other hand, looking at some models of field theory on a Moyal, Dorothea Banz found that, well, there is some remnant of causality at large distances, so-called cluster decomposition property, for the expectation expectation of some propagators, so some endpoint functions. Then there's been some propositions for the alternative to macrocausality, which is called theta microcausality, theta locality. So the idea, to go behind, to extend locality to some other notion. And there's been also some proposals to, well, make the noncommutative theories in a way from the beginning local. So not to start with general noncommutativity, but to start with some sort of deformations which are on the so-called wedges, which are then replace, the notion of locality in the field theories. What of that is true? What of that is significant? Absolutely, I have no idea. There are 2 points, so is there way out? We don't know what's causality at a small scale. So the good answer might be probably to look for causality for the quantum field theory and then dwell something for the other. Now, we don't know whether the gravity at a high scale, at the high energy scale, is compatible with causality. Now, if we admit noncommutativity, can we think of time as noncommutative, some operator? Do we need Lorentz symmetry? Do we need deformed Lorentz symmetry? How to construct quantum field theory for the noncommutative geometry? And finally, the question is the way to test it. And okay, I can give you only my personal beliefs. My personal beliefs is that much of this is untestable. So the only thing, that one can think of are some, so to say, interpretations of the models that could be applied to observations. All right. Just 2 last words. So I would say that then noncommutative geometry is just a set of tools and ideas and some models, some examples. It's more about the language and more about the mathematical ideas than the real description of a space. It's just like a setting ground for the description. So far, the description of the world is based on differential geometry. This extends it. Whether it's good or wrong, future will tell. But this is the extension that goes into the maybe right direction. Some idea still needs to be developed, so there's a lot of work out there. Maybe causality is not a good notion. Maybe one needs to think about it. There are some ideas to links to physics, and as a sort of advertisement, I'd like to tell you that in just 2 days, there will be a small workshop where the chairman will actually be the speaker about the links and the applications of all these ideas to cosmology and physics. Thank you very much. Sorry for taking more time.
information. On the other hand, in the Lorentzian case, it seems that the spectrum doesn't contain so much information. So how? Well, it seems that it's just continuous. That it's just.
No. The question, I mean, so the difference, the continuous discrete, is not really Lorentzian, because you can make the compact manifolds is rather compact and not compact. Because the spectrum of the Dirac operator in the Euclidean case could be also continuous.
Right. So,
it's just.
Let me phrase it in the following way. So
yeah.
Certainly, to every statement which I will try to make now, there exists a counterexample. However, generically, when Alan Kohn, so generic example of Alan Kohn's theory is an example when the spectrum is discrete.
Of course.
So that we have a set of numbers, and there may be many different sets of numbers. So in this set of numbers, this countable set of numbers contains huge amount of information.
Yes.
On the other hand, in Lorentzian case, somehow for generic example or sufficiently large class of examples, the spectrum is just a line, and it doesn't seem to contain much information. So the question is, how can you overcome this problem and still use some information from this spectrum?
Okay, so in the Lorentzian case, for instance, you can make a torus. So you can make compact manifolds Lorentzian. So this is example is a torus or a three-sphere. So three-sphere is a fantastic example of something which is compact and can be made Lorentzian. And then the spectrum of the Dirac operator is actually discrete. So it's not these are not isolated points. But the spectrum is also parameterized by some integers, and you can still get a lot of information from the spectrum. Of course, the point is, not by this method. So the thing is, okay, if you're saying there's not an easy way or not way yet discovered to recover this information from the spectrum, but the spectrum is still discrete, so you can still parameterize the spectrum, and then using this argument of, say, well, Wick rotation, whatever, or this Lorentzian spectral triples, you can make a passage from the Lorentzian case to the Euclidean case, and then you recover the information. So this is roughly the thing. So
this passage somehow, in some magic way, makes lines some spectrum which consists a lot of new information.
No. The spectrum of Dirac on a three-sphere, for instance, with Lorentzian is not a line.
I see. So this is only the okay. But in the infinite case, in the case of cosmology, which has infinite time-like slices, then.
Oh, okay. Answer what you mean. The point is, for instance, if you take all the spheres. So classically, Riemannian spheres. The spectrum is always. The spectrum alone, without multiplicities, is always boring. Almost. For the spheres, it is always the same. The question is the multiplicities. So like the density of the spectrum. So in the continuous case, it would be like the density of the spectrum, and then the density of the spectrum contains the information. Yes.
I see. Okay. Thank you.
Yes, I have a question.
Thank you very much. I think I'm beginning to understand what noncommutative geometry is about, that it's a change of language to some extent. Now, could I just confirm, the key thing at the moment seems to be translating, before we go to Lorentzian cases, Riemannian geometry into algebraic language. And
yes.
I don't know if you heard my talk, because we had to swap because there. But the thing that I would be very interested in is whether you can do, what happens if you try the same trick of changing the language if you start from a conformal three geometry or conformal geometry where there is no notion of distance, only of angles, and you did the same thing there. Has there been work done in that direction? Because I would be very interested to know about that, and whether in that case does something like a Planck length emerge in, I think you understood that when you take the inverse of the Dirac operator, you said that was like a...
Well, this is like, it's not like a Planck length. It's something like what one can say is a sort of a line element. Because, this D...
The inverse.
Yeah.
Yes.
But it's not actually, I mean, because I mean, if you take a sphere, for instance, I mean, there's no minimal length, and still, you know, the universe makes sense. I mean, it's sort of there's the, so to say, the biggest eigenvalue of the universe and so on. So it's not like a Planck length. But I mean, answering, you know, to your question about the conformal, say, type of geometry, when there's no notion of distances, only, say, angles and something like that, and then it's been developed to some extent. There's one work which goes in this direction by Christian Baer, which makes the sort of description of conformal geometry in this language of spectral geometry, but I mean, just adjusting it. So there is something in this direction.
And you would have something analogous to this inverse of the Dirac operator, which seems to be the way you would be perhaps making some contact.
Yeah, I don't
with
recall. I don't remember it, but yeah, there might be. I mean, this is. I think. I mean, the good reference. I mean, to look up is Christian Baer's paper. It has the word certainly conformal and noncommutative in it. Yeah.
Thank you.
Yeah.
Thank you very much.